Section 2.3, the dot product. The dot product is a mathematical operation that came out of necessity. We're going to investigate a case where we're trying to calculate how much of one force is being applied parallel to another force. And in that case study, we're going to discover this operation, the dot product. Sometimes a force is applied in the exact same direction as the object that's moving. That's a very simple case. But sometimes it's not. That can happen in 2 dimensions, like we see here. We have cars that can move on a plane. One car is bashing into another, and it's causing movement in a direction different than the force that was applied. I have another image here. We have a sled being pulled across snow. The man pulling the sled is pulling at an upwards angle. Gravity's holding the sled flat on the ground, and so the motion that's being caused by this force is parallel to the ground, even though the force is at an upward angle because the man pulling the sled is taller than the part where the rope attaches to the sled. Or maybe even pushing a car. You can see the child pushing the car is leaning in, and the force that he's applying is almost parallel to his body, but the car is moving across a level surface. So the motion is parallel to the ground, even though the force is being applied at an upward angle because of the height of the child. Let's get back to talking about vectors. We're going to start back with the 2-dimensional case because illustrating in 2D through a 2-dimensional screen is much easier than trying to draw it out in 3D. So we'll start with talking about it in the 2D case, and then we'll extrapolate to 3D. On the screen, you see 2 vectors. They're both being represented with directed line segments. One vector I'll call F, the other vector I'll call V. The F vector is the force. The V vector is the vector pointing in the direction of motion. We want to know how much of the force vector is actually being applied in the direction of V. Essentially, we're going to create a right triangle using the tip of the force vector dropping a perpendicular down to the V vector. The amount of the force F that's being applied in the direction of V is represented by this hollow red arrow. That is the portion of F that's perfectly parallel to V, and we can see that in the image. The length of that vector, the amount of the force, we can use trig to find that. So remember that with a right triangle, which is what we have here, we have our 3 trig functions. We have sine, cosine, tangent, and each one of those takes in an angle and then spits out a ratio of 2 side lengths. Now, some of us use SOHCAHTOA to remind ourselves what the side length ratios are, but I can't spell for the life of me, so I can't remember which one has the A and which one has the O. So I use a slightly different mnemonic device. I spell it out with a story, and my story goes, some old hippies came a-hoppin' through our apartment. So that's how I spell SOHCAHTOA. And it helps me remember that the sine function is a ratio of opposite over hypotenuse. Cosine is the ratio of adjacent over hypotenuse. And tangent is the ratio of opposite over adjacent. If I have the right triangle, which we have drawn on the screen, and I'm looking for this bottom side of the triangle, if I were to know the angle between my 2 vectors, let's call that angle theta, then I'd be able to find that third side simply by using trigonometry. I know that the vector F makes up the hypotenuse, so the length of that vector, the magnitude of F, would be the length of my hypotenuse. So I would be able to put that in place of the hypotenuse, I'd use the angle between f and v, and with those two facts and the cosine function, I could find the length of that missing side. That all seems simple enough. However, what if we don't know what the angle is between f and v? If it's not given to us, can we find it? And the answer is yes, we can. To be able to find that angle, I need to go back to something that you might not have seen for a long time, and that's the law of cosines. Now we know that there are nice right triangles out there, and we also know that there are triangles that don't contain right angles. We call those scalene triangles. None of the angles are equal to 90 degrees. The law of cosines helps us to complete all of the measurements for those types of triangles. We can find the length of any side or any angle within the triangle using this law. So what we're going to do is create a triangle that matches these two vectors. So I'm not going to use the perpendicular line here. I'm going to use the entire vector v, the entire vector u, and I'm going to connect those to make a third side using angle addition, or angle subtraction rather, adding the opposite of u. So now I've created a triangle that's made up of three vectors. I have one vector that is the vector v, that's one side of the triangle. U makes up a second side of the triangle, and then the vector difference v minus u makes up the third side of this triangle. And visually, we can see that I've made this triangle so that none of the angles look like right angles, which means the Pythagorean theorem will not work here. I'm going to copy this over and remind you of what the law of cosines looks like on a regular triangle. Now, when you learned about the law of cosines, you probably labeled your angles with capital letters and the corresponding opposite sides with lowercase matching letters. So I have angle A down here on the bottom left, and across from it, I have side A with a lowercase a. So we're going to compare the law of cosines for the triangle in blue to the vector image that we have on the left. I want to make substitutions so that I can use the law of cosines without using a, b, and c. Instead, I want to use the vector v, the vector u, and the vector difference v minus u. So let's make some comparisons. First thing we might notice is that the angle A is in the same position as what we're calling theta. So we can easily replace theta with A. Maybe we also notice that side C is the same side that's made up by the vector v. Now let's be careful. The vector v has more than just the length that's tied to it. So when we talk about C being compared to the side made up by vector v, we're talking about the magnitude of v. Those two things are equal. So the side C is equal to the magnitude of the vector v. Same with the side B. That's going to be equal to the magnitude of the vector u. Side A will be equal to the magnitude of the difference between vector v and vector u. And if we look at the law of cosines as it's written with A, B, and C, we see that it involves the angle A and the letters A, B, and C. So we've been able to make the connection between our vector image and the other image completely so that we can replace all of the values in the version of the law of cosine that's written with our vector version. So instead of a squared, I'm going to use the magnitude of v minus u squared. That would be equal to, instead of b squared, I'm going to use the magnitude of u squared. Instead of c squared, I'll use the magnitude of v squared. I'll have minus 2 times b, which is the magnitude of u, times c, the magnitude of v, times cosine of what was equivalent to a, which is our angle theta. Now, we'll be able to solve this equation for theta. That's our goal here. If we're given the two vectors v and u, we'll be able to complete every value in this equation except for theta, which means that will be the only unknown, and we'll be able to solve the equation for theta. Now that we have the law of cosines written out using vectors, we can solve this equation for theta. It's going to require a lot of algebra, and I actually encourage you to try this part on your own. I'm going to work it out, but maybe stop the video, give it a shot, and see how far you can get, and then come back and see if your work matches what I've got. The first thing I'm going to do is expand each of the terms that involve a magnitude squared. And I'll do that by allowing v to be written in a general form. So I'm going to pretend like v is a 3D vector, which means it'll have three components. v1 is the first component, v2 is the second component, v3 is the third component. And I'm going to use the same idea for the vector u, except for the components will be named u1, u2, u3. So let's write out each of these terms in expanded form. After we've written out each of these terms in expanded form, we can replace those magnitude squared terms with the equivalent. Now, this does not really look like it's going to make things easier on us, but trust me, it will. Notice that on the left-hand side, we have the magnitude v minus u squared. And then on the right-hand side, we have magnitude u squared plus magnitude v squared. So these terms, the magnitude of u squared and the magnitude of v squared, are going to balance out with some of the terms that appeared on the left-hand side. And we'll know that after we expand each of the binomials out. So unfortunately, we need to do even more algebra. I'm running out of room, so I'm going to copy what I have down and then resume. I've copied the calculations that we just did, and now we need to multiply out the binomials in this first expanded term. So if you remember how to multiply perfect square binomials, this can go much faster for you. I'm going to go ahead and write it out. All right, so we have all of the terms that come from expanding out those binomials. Now, I made the comment that this term is going to balance out with the other terms that are on the opposite side of the equation. Remember that if there's two terms that appear on both sides of the equations, we can simply subtract from the whole equation and eliminate those terms. For example, v1 squared shows up on the opposite side of the equation. So when I subtract v1 squared from either side and to both sides, those terms both go away. Same thing will happen for u1 squared, since it shows up on both sides of the equations. v2 squared, u2 squared, v3 squared, and u3 squared. So the magnitude of v minus u squared basically took out both the magnitude u squared and the magnitude v squared. But we have some terms left over on the right-hand side. So after we've eliminated any of the balanced terms, on the left-hand side we have left and on the right-hand side, The only term that's remaining is the negative 2 times magnitude v times magnitude u times cosine theta. Now we do have calculations that have expanded these two magnitude terms, but we're going to leave them as they are. For now, you'll see why. Taking a look at what's going on, we want to solve for theta. That's our ultimate goal. So let's take a look at the common factor, negative 2. We can factor that out. And that allows us to divide both sides by negative 2 to simplify just a bit more. So now we have, oops, I've factored out a negative and I forgot to make sure that my signs matched accordingly. Those should be positive terms. And that's equal to the magnitude u magnitude v times cosine theta. And we're going to pause right here because our goal is to solve for theta. And everything that we have, the vector v, the vector u, all the components of each of those vectors, it's showing up here in the equation. Now, we have names for the calculations on the right. Those are magnitudes of vectors. What we don't have is a name for what's happening on the left. And this is an important observation. If our goal is to find the angle between two vectors, and no matter what two vectors we're using, we have to compute this calculation in the yellow box, that's a significant calculation. It's an operation that we should probably define since we're going to use it going forward. And so that's exactly what mathematicians did. They called this the dot product. Another name for that is the scalar product. It's called a scalar product because this operation, which involves each of the components of two vectors, produces a scalar. Remember that the vector v had 3 components in its definition. The vector u also had 3 components. But when we're calculating what's in the yellow box, we're breaking those components out of the vector notation, and we're using just the components and addition. So these are just numbers being multiplied and added together. So this operation, the dot product, also called the scalar product, will take 2 vectors and produce a scalar using the components of those 2 vectors. We just discovered the dot product, and now we want to try to use it. The notation for a dot product between 2 vectors uses a dot. Now this is similar to the dot that we use for multiplication, and it's often easy to get confused. Is that a dot product or is that a multiplication symbol? The only way to answer that question is to ask yourself, what is to the left and right of that dot? If we're talking about 2 numbers, then that is regular multiplication. If we're talking about 2 vectors, then we know it's the dot product. When I teach this class face-to-face, I play a game called, is this a vector or a scalar? And I'll try to play that through this video, but it's going to feel a lot like Blue's Clues, where I'm talking to you and you're not talking back to me, but I'm going to pretend like you are. So if you look at the expression u dot v, and you're not sure is this a dot product or is this multiplication, just look to the left and ask yourself, is this a vector or a scalar? And look to the right. Ask yourself that same question. And it's important to ask it for both left and right because you could have a scalar on one side and a vector on the other, and that's where it gets the most confusing. In order for it to be a dot product, it has to be 2 vectors. So in this case, where I have a scalar, like 3 times a vector, which is v, this is scalar multiplication. not a dot product. The only time it's going to be a dot product is if you have a vector and a vector. So let's go ahead and calculate u dot v, where we're going to have the general form of the vector u multiplied to the general form of the vector v using the dot product, which is literally saying to multiply corresponding components. So take the first component of the vector u, the first component from the vector v, multiply them together, and then repeat that for all pairs of corresponding components throughout the two vectors. Let's give it a shot. If I have the vector u given by 3, 5, 2, and the vector v given by -1, 3, 0, then to compute u dot v, I just need to multiply corresponding components. So I'll multiply the x components, 3 times -1. Then I'm going to add to that the product of the y components, 5 times 3. And then I'll add to that the product of the z components, 2 times 0. And then we'll simplify. Notice how we started with two vectors. We applied the dot product operation, and the result is a scalar. So now it's time for that vector or scalar game. We are confident that this is a vector, I hope. We are confident that this is a vector, I hope. But now when you see u dotted with v, two vectors dotted together, I want you to make the association that that is a scalar. So if we're playing the vector scalar game, if I'm talking about u, you would say vector. If I'm talking about u dot v, I would say scalar. Let's try another one. This time let's calculate the scalar product with two vectors that are not written in component form. The vector u has components 10i minus 4j plus 7k. The vector v has components -2i plus j plus 6k. Now, if you watched the last videos where we talked about standard unit vectors, I said that I, j, and k should have hats because they're unit vectors. Now, I'm not using incorrect notation here. They are vectors, and an arrow on top simply denotes that we're working with a vector. A hat might be more specific, but it's not really incorrect notation here. All right, we want to multiply u and v using the dot product. So to do that, we just need to identify corresponding components and multiply them together. So the I components are corresponding, we'll multiply those. Then we'll move on to the j components. Those are corresponding, we'll multiply those. Now this j in the v vector doesn't have a number in front of it, so remember there's like an invisible 1 there. And then lastly, the k components are corresponding, so we'll multiply those. And then simplify. Again, we computed a dot product, and the result of that dot product was a scalar, not a vector. So please burn this into your brains. The operation, the dot product, starts with two vectors, and after applying the operation, results in a scalar.